And there's another which is called rat finite. So it's definitely very interesting to understand not only conformal infinite, but just doing continuous infinite. It's just hard. And then I have a little problem of stability if you want to realize in nature. So another question. So now I want to explain the anyonic chain. So the anyonic chain is a very simple thing. So pick any anyon model. So this is your universe of anyon. Find many types and simple object model anyons. And there are two versions. There's an open version chain, there is a closed version. Let me do the closed version. So what you do is you take an anyon model, you pick a particular type of anyon. Let's call them J. And then you draw this circle with some edges out. And remember, anyon has a fusion rule. So you want to build a Hilbert space by fix these anyons. And then you label the edges of the circle by other anyon type, with the constraint that for each trivalent vertex, that's a legal fusion. Okay, which means take any two, the third one should come out. There's a little symmetry thing, but that's not that. And that's the Hilbert space. So the Hilbert space is depend on the J, fixed J, and then all the legal labeling of fusion tree, and that's what the normal. And then your Hamiltonian can be ferromatic or anti-ferromatic. You just take any two neighbor and you fuse it, and then will come out some other anyon. And if I take J to be -1 to do the anti-ferromatic, I want the energy of a fuse to the vacuum as the lowest energy. So that's my Hamiltonian.
You said the input is anyon model, but does this depend on the gradient structure at all?
Anyon model has a gradient structure. So basically, the definition is independent. That's another thing. I'm not 100% sure I agree with some, published work, which is, can you get a conformal field theory for a fusion category with no gradient? I don't believe it, but there are papers published already saying they do. So that's a different discussion, but that's a very interesting question. The reason I can just tell you why I don't believe that statement. So if you want to get a conformal field theory, you need a lot of symmetry. And the one important symmetry is the gradient give you a full gradient. That's a translation symmetry. It's hard for me to sort you can get a conformal field theory without translation symmetry. So that's the abstract model. And now, let me give you an example. Again, this is again a map thing. So I want to talk about the example of SU2 level K. So if you take the SU2 level K model, so this is the SU2 level K can be three different things. Can be a Church-Turing theory, can be a model tensor category, can be a WZW CFT model. So let's take this as the anyon model. And then the spin half irreducible representation is the fundamental anyon. And that's the chain I will build upon. And then I have the internal degree freedom, which are other irreducible representation, not truncated. And I can just do exactly what I said, write out the Hamiltonian with a -1. And this is the anti-ferromatic version. And then you realize something very interesting. This Hamiltonian local term is proportional to something called the Temperley generator. So the Temperley generator is normally noted by EI. So this is the incredible algebra appeared in such a solution of the 2D Ising model. And what it is it fixes the integer n. It's a Temperley algebra n has E1, E2, En -1. And then the algebra is EI squared with EI. D is this very important number. And then EI is a neighbor, then EI is go back to EI. I can easily check this by look at this picture. And the EI represented by a straight line, and then this I plus 1 given by this colored cap. And then you stack them together. Every time you see extra loop, that's equal this number. And that's this Temperley algebra. So this SU2 level K Hamiltonian is closely related to this Temperley algebra.
Is the SU2 WCW the continuum limit of that?
Is that
The continuum limit of that is the WCW?
It's not quite, but almost. It will go back to the coset. That's what I got.
But it's automatically gapless.
It's gapless. That's the main thing I want to explain.
Okay.
is Y gap is Y stable. So basically, you can now imagine the following: you have anyons in your ring, and just ask, I put one anyon, what it convert to, and that's actually will be the paper which this paper I cited. So it turns out this will become gapless. You can do on the computer. That's what we did. It just uses the Carty formula. The energy is some non-universal constant, and then 2 pi over something, and then the central charge, the scalar dimension. You just do the formula up to length 36. You see beautiful scalar dimension come out of it. There's no doubt about it. And if you have this kind of limit, then you can ask why it can be stable. And that's one of the arguments to many people. The only new thing in the paper is this topological symmetry. And Matt is here. He wrote an incredible paper with Andrei Gromov to explore those things. I think he knows more than me about this limit of those topological symmetries. So those topological symmetry is a very important part of the stability of the conformal field. It's not enough to protect it, but without it, there's no chance. And so now I want to explain this topological symmetry, because I believe this is the first time in lattice model we have generalized symmetry. It's not improved or anything. It's just generalized symmetries. So the way to see this is very easy if you use the formulas of topological quantum field theory. So I said the anyon model is a unitary model times the category. It's a theorem of triad. Every of those things leads to a 2 plus 1 richly triad TQFT. So there's a TQFT behind it. And now you imagine a torus puncture, and then you label each puncture by the anyon type you choose, the G. And the TQFT is extended 1 dimension lower, so there's a Hilbert space for that. Now that's the Hilbert space I told you, the constraint labeling. So that's the Hilbert space. And then you draw the tree, that just, you take a specific basis for this Hilbert space. And that basis is very special. Okay, that basis is the conformal block of the corresponding conformal field. So that's a special basis. It's a conformal block basis. And then, if you think about this way, the topological symmetry is very simple. You have the torus with the punctures, and then you imagine you have a book, and you have a Hilbert space. You can either book, you can draw any anyonic line, and label by anyon, and then fuse to this anyonic tree. It's the same theory, is consistent, so it's better to be compatible with the Hamiltonian. And that's the topological symmetry. And that topological symmetry ruled out a lot of relevant deformations. And that makes the anyonic limit stable. That's converted to conformal field. So that's pretty much the anyonic chain thing. Oh, maybe I can talk. Yeah, so I can set up my computer.
Sorry about that.
I thought it would be better.
Yeah.
Sorry, my computer is just Microsoft is complicated, so sorry, just
Does someone have an adapter by any chance for HDMI? USB-C? Oh, yeah, sorry. USB-C, right?
sorry. It's just that my computer belongs to corporate. Corporate computer is very difficult to set up. Everything's wireless. quite curiosity. This has been around for a long, long time. When Wang got his field medal by rediscover the Temperley algebra, discover the quantization of Jones index, and it's come with a sequence. And for all those we know minimal model, there's also a sequence there, and they are very close related. You might ask, what's their exact relation between the Temperley algebra and the Virasoro algebra minimal model? So I was fascinated by this question for a long, long time. I don't know what to do with it. Just formally related to the same subject, they come with a sequence. And the answer actually turns out is something really beautiful. And the name of Q formula. Unfortunately, the bad news is it won't work. So let me tell you the subtlety as your colleague. So if you have these two algebra, the Temperley algebra is just, as I draw it, the definition, just part of a finite lattice thing. And the Virasoro is the simple extension of the weighted algebra of vector field. And obviously, it cannot be exactly the same. One's finite, the other is infinite. And it turns out, he might be student there, they discovered that if you take, doesn't matter which way you go, but if you take the field transform of the Virasoro, and then you truncate the coefficient in the right way, and that would be the version of Temperley algebra of the lattice. So that's what it should be. And more than that, this is the paper. And more than that, they write out exactly formula for you to start with the Temperley generator. And then, in order for you to get to the Virasoro, which is real, you need to also add its derivative, so that's the commutator. And then you have some coefficient, you need to rescale the ground state energy by the central charge, so that's a little minor. And that's what gives you a beautiful formula. If you do numerically, it will convert to conformal field.
So if I add L0 plus result, it equals Hamiltonian result.
That will come, yeah, that Hamiltonian also come L0, yeah, just take 0, that will give you the L0. So that's what they did. And the subtlety is that if you want to do analytically, if you really want to see the convergence, and then I will come back to this slide. I did a version without knowing that, so I'm a very good student. I just said, let's do the convergence, set up an internal coefficient to see what the coefficient should be. Then we found a formula slightly different. Instead of a J plus 1, we plus a half. If you think what Temperley is like, where the Temperley algebra general sit, so they're sitting here at the integer lattice, we shifted to the middle. And I was very happy because I knew Poussin's formula cannot be correct analytically. Because if you do the commutator, and the central charge will come out wrong. And then Sarah came to Santa Barbara to tell me, you cannot be correct either, because I can show my formula converts the same thing as his formula. And the only thing better is my formula converts faster. But in the end, they're the same, so this is also the wrong formula. So numerically, everything works perfectly. It's just that there are many things goes to 0 limit, you don't see it. But the things even worse. The 0 sequence can convert to non-zero. That's what subtle lattice model to continuous is. That's the problem. 0 can convert to non-zero. So the thing so bothered us. So Hubert asked his student in here, they're gonna hire her as a postdoc, try to do numerics. And he got this formula. She got this formula. So the central charge, not the one you quite want. There's something else here. So this is the status. Nobody knows. I mean, Hubert and I. We have lots of discussion, we just don't know what's going on. But the phenomenon is the following, is there are lots of states on the lattice. There are no corresponding states in the continuum. We have no mechanism to pick them up. Although we invented a name called scaling state, but we just don't know how to define them and define the lattice. So I'm 100% convinced there's something We just don't know what it is. Correct. So that's I consider this a extremely interesting question analytically. How can that be so close to be correct, but it's not?
But you can fix sample charge from just Jacobi identity. So there is only one sample information of the resource.
This is not derived. This is a numerical fit. This is
Yeah,
not.
but then we can redefine else a little bit such that you get one sample
Yeah,
charge.
if you want to force it into the algebra, then you will force it. But I'm saying that this is not a statement. This is a statement of Q-Steller formula. You just take the Q-Steller formula, you do numerical simulation, and then fit the data. You won't get to the correct central chart unless it's level 2, which is free Fermi. And the off is rest.
So is C star anything interesting, or what is this number C star? Is that interesting?
This what number?
The
C
one,
star?
yeah.
I think it's very interesting.
What it can?
I don't know. My speculation is we definitely choose the right co-cycle representative most of the time, but co-boundary theory you can always add in. So I don't know. I don't have, but I actually personally believe there's a deep physics phenomena related to this one. So this is the numerical experiment. So Stephen Q did a lot of them. I think maybe Matt also did. I think a lot of people did record simulation. It's just that analytically we have a serious problem, which is how to make that conversion. So I want to make an assumption to do the limit. So because I want to do mathematics, so at a finite state before limit, I don't want you to have a given dimensional Hilbert space, because that's just not easy to do mathematically. So I'm always finite. And then the subtlety is pushed to how to take the limit. Just to tell you, the subtlety, if you say, oh, take the lattice z squared and then put a qubit on each of them and take the limit of Hilbert space, that's a very difficult question. It's not well defined in general, mathematically, because it depends on the infinite boundary condition. The right way to do it is using GS construction. So that's, I'm just sort of saying the subtlety of limit is pretty serious. And the paper I wrote with my student came up with a mathematical definition of this scheme limit, which is that in order for you to do the limit, you take the final lattice Hamiltonian, diagonalize, and then you truncate all the high energy part, only focus the low energy, take a limit, and then let it cut off, go to infinity second. So it's a double step. And so that's what we get. And then as you see here, this Hamiltonian convert to L0. And then this will get correctly. And we can prove this only analytically for level 2, which is free Fermi. And this one, we can rewrite the anyonic chain model using Majorana fermion, and then we can completely diagonalize the Hamiltonian. Everything converts beautifully analytically. So this is the only case we can do analytically because we know Majorana fermion diagonalize the anyonic chain. And I have no doubt about this conjecture that if you take the 1/2 fundamental representation truncated in SU2 level K, you do the anyonic chains convert to the minimal model. And the next one is a beautiful case, it's convert to the triple vertical IZ, central chart 710. And that's the numerical simulation is about. It's definitely there. And I would really love to continue this. Actually, I was talking with Hubert last time. He said, you should quit your Microsoft job just to do anyonic chain. I don't think anybody will pay me as well. So it's a beautiful problem to understand this in a more analytic physical way. So now I want to move on to the thing I'm excited recently, which is I cannot prove anything, but I have no doubt about the convergence to conformal field. And now I want to say if this can be generalized to high dimension. And many people will immediately object. This is the thing that in 2 dimensions, we have an infinite dimensional conformal symmetry grouping. In 3 dimensions, higher, we all have finite. But I think that's definitely correct, but in the age of everybody's talking about generalized symmetry, we need to think a little bit outside this Lie group symmetry thing. You might want, if there's other symmetry you can introduce. So the first thing I tried is this fusion surface model, which is supposed to 2D generalization of dynamic chain. I don't see any evidence will converge to conformal field. So in the end, I decided to pursue something called the fuzzy sphere model. And just to, if I, go on there, so the way I'm thinking is that if you think of the Minkowski space, right, D1 and compatible, and that will be SD process 1 with a Z2 function. But I'm going to talk about linear algebra, so forget about all this finite cover for the moment. It's not that not important, just my theory is not that good to even tell the difference. So let's talk about linear algebra only. And then another way to see the left mover and the right mover of conformal field theory is this compactification. For one dimension is S1 plus S1, and the diffeomorphic group of S1 plus S1 is 2 copies of S1. Now if you go higher dimension, you think about the diffeomorphic group of S2 plus S1. This is extremely interesting infinite-dimensional group. Most of the infinite-dimensional group they homotopic to finite-dimensional U. This is the first one, simplest, not homotopic to a finite-dimensional U. So this is some kind of generalized symmetry. I will tell you why it's not. So that's basically I want to explore, which is some little bit of generalization not related to finite-dimensional U. So basically, I want to claim the following. There is a fuzzy sphere algebra. It's very close to the Temperley-Lieb. And I want to explore this group, which is lots of things, which is the area preserving diffeomorphic to two sphere. Not all, just area preserving one. And then I need to do the loop extension because I want to get non-trivial central extension. Without it, you don't have it. And this relies on a theorem due to Hatcher, which is the diffeomorphic group S2 plus S1 is homotopically to those three things. So the homotopic type of diff S1 to 2 is the diff S1, which is homotopic to O2. This is O3. This is just the 3 sphere, and then the loop group of SO3. And this has cohomology in every given dimension. That does not happen for finite dimensional U. So this is basically cohomology like CP infinity. So that's the interesting part. So that's basically I want to explore, which is, are there 3-dimensional conformal field theories has symmetry this long? And it's not clear, but I want to argue there is a possibility here. So let me remind you the fuzzy sphere. So the fuzzy sphere is defined by using non-commutative variables, but I think the easy way for me is that it's a mathematical theorem that a 2-sphere is the limit of all n by n matrices. That's a mathematical theorem. And the way you see it is, using mathematics, the 2-sphere is the same thing as all the functions of the 2-sphere. And then you recover a point by using maximal ideal inside this algebra. And then you approximate this abelian algebra infinite-dimensional with a finite-dimensional algebra, and that's convergence. It can be defined mathematically. And just to show that this is subtle, you can also take this one, convert to the torus by choosing a different way to do it. That's also fine. I think you can convert probably to every surface. Gamma, I don't know, but 100% can go to torus. And if this is the finite 2-sphere, and then this will be a symmetry. And then this converts to the area preserving diffeomorphism of the 2-sphere. I'm not 100% this is a mathematical theorem, but it's definitely established in physics. So that's the one I want to explore.
So in this second, what's the meaning of it? What's the limit?
So it's in the sense of linear algebra. So the theorem is basically the following. I have mentioned it, but if you take the linear integrate to 0. And there's a Poisson bracket. And you can take this Lie algebra, and this Lie algebra will approximately convert to that Poisson Lie algebra.
As n goes to infinity.
Yes, go to infinity. I'm not 100% sure this is mathematical, but this is well established in physics.
Can I explain a little bit more in which precise sense the S2 is the limit of the matrix algebra?
Yeah, so this is actually a mathematical theorem. So what it is you take all the functions of the two-sphere as a unidimensional abelian algebra. And then you know the points on the two-sphere corresponding to maximal ideal of this algebra. And then this matrix algebra, if you define the right Gromov Hausdorff dimension, will converge to that algebra. So that's about it. This is a quantum metric space. So that's the. So why I like this one? So this is a philosophical point. It's very difficult to discretize the two-sphere. The circle is just described by polygon, it preserves symmetry very well. Two-sphere, we know there's no group to approximate the two-sphere. So what do? I think this is the best finite approximation to have symmetry. So the way I want to use this is use a paper by Zhenghan Wang, which is incredibly interesting, is the following. So they take the following physics situation. They take a monopole of a flux 4 pi s, put the origin, and then we imagine it's a two-sphere of some radius. You put a single electron on this two-sphere. And that's a famous Landau problem. The electron have Landau levels. And the lowest Landau level is a very interesting degenerate space given by orbitals. And then you write down Hamiltonian using only these orbitals. And the Zhenghan Wang did is for each orbital, they put 4 degrees freedom there. And we write down this Hamiltonian with like 16 electrons. They see the scalar dimension of the 3D Ising model up to 1%. This is far from the bootstrap, but this is only 16 electrons. You can do all that one. So that's the beauty of this model. And if you change the Hamiltonian a little bit, you probably can get free scalar, other ON model, all the others. So that's what I call the fuzzy sphere model. It's just you take these n orbitals, you put degree freedom on them, you write out Hamiltonian, and the beauty is this preserves the SO3 symmetry. So that's what I call a generalized speed chain. It's just a chain of circles, and you write down interaction between them. And numerically, very strong evidence this will converge to conformal theorem. Like a 3D Ising model. And the analog is pretty straightforward. If you write down the projected electron field on the two-sphere, project the lowest Landau level, and that forms some algebra that's very much like a Temperley-Lieb. But turns out this is hard to work with, so I want to go to the momentum space, and that's what we did in the paper with Louisa. So here's the beautiful way to do the momentum space picture. So you take the sphere harmonics, and then you realize you can turn them into matrices. So you turn a spherical harmonic into an operator by using this definition. So you take the spherical harmonics, you make it into a matrix. After this normalization, this is just a Wigner 3JS symbol. And then these matrices give you a new basis, basically, of the SUN, like a UN. Okay. So it's just a word string basis of UN in finite dimension. And then you use these matrices to write down the interaction of electrons spin up and spin down. And that's actually the main ingredient of the fuzzy sphere model to get a 3D Ising. But I'm not doing the 3D, I want to do, but at this point I'm just doing. So this is a finite dimensional operator. And it's using the quantized sphere. And you can ask if this has good algebra structure. And it turns out, Yun-Chen wrote down this commutator. And I didn't never ask him how he did it. We will derive this commutator. And the first contribution I made with Louisa is we show that this indeed is a Lie algebra. So this is indeed has the typical identity. So this is the momentum version of the electron operator project to the lowest Landau level.
But this is true for any value of the parameters you have in the Hamiltonian, right? Why
These have no Hamiltonian yet. This is, so the Hamiltonian,
the Ising arrive is only for specific choice of parameters
Yeah.
in the Hamiltonian. This is true for just the density operators, right?
this is just your single density operator, and then you do the momentum, the Fourier transform. So the Hamiltonian will be many sum of those things. And the coefficient would be, the fine tuning would be the coefficient in front of those operators. So the Newton-Hurst Hamiltonian would be like a quadratic in this N, A, and D, with coupling constant.
Yeah, I know, but the symmetry that you are claiming arises should arise only at the CFT point, right?
Yes, that will come. This will only be in the limit. The final have no limit. But this is not even, this is just a rewrite of SUND algebra in a very strict basis. To answer your question, what I want to do is take the limit of this sequence. And I want to kindly go to something I want to. At this point, there's no limit as anything. I'm just claiming.
I think this is just a property of these density operators. You haven't put them together and coupled them in specific ways to generate the CFT spectrum yet.
I'm not doing anything like that yet. That will come later, but I'm not done anything like that. At this point, it's purely about this operator has the algebra structure. So that's my first thing. I want to say there's something analog to complete. Then I want to say what is the generalization of Virasoro? And here's the one I want to propose. So if you take the ever-preserving diffeomorphism, and there are two groups here which we wrote out. One is this one, and the other is the diffeomorphism of the two sphere. They have no central extension. So that's why we don't study them. The only one we have non-trivial central extension is the loop algebra of area preserving diffeomorphism. That's the only one has non-trivial central extension. And we calculate the cohomology, that's one dimension. And we can write down the co-cycle generate this generally. So that's, I will focus on this algebra, which is the loop algebra of area preserving diffeomorphism. And that's my proposal of a analog of Virasoro. Now back to your question, how do I put this together to get a limit? And I don't know, but let me try to convince you there is something here. Oh, there's one more thing before I do that. Another theorem in this paper is that if you take the loop SUN, and there is this co-cycle from the Killian form extended to the loop, that one converges to the one we discovered if you rescale by 6 over KT. So that's given the connection finite to infinite. So there is co-cycle convergence.
Can I ask a question?
Yeah.
On some previous slides, the relevant group was the diffeomorphisms of not just of S2 but of S1 times S2.
Yeah, I will come back to that one. Yeah, that's a serious problem. I will come back to that. So so now I think I'll still end up on time. So let me try to convince you this is not everything, nothing there. So if you think about the anyonic chain, and there's a beautiful way to see it, which is a generalization of the so-called Shor-Weil duality, which is repetition of SUA and SA are due to each other. And the same thing happens on the anyonic chain. The anyonic chain comes from SU to level K, and then there's a Temperley algebra. They are due to each other. So one kind of generating the states, that's the spectrum of generating, the other is the symmetry. So that's why anyonic chain works. And here I want to say, this is how it works here. There's a Fudge sphere, which should give you the Hamiltonian put together, and then there's this area preserving diffeomorphism supposed to play the role of symmetry. So I cannot tell you there's any, there are some evidence there is this limit thing, but as we will hear for the next talk, to do any distant mathematics is extremely hard. It's beyond any hope I can do. So, but there are numerical evidence. that this is a possibility. So now let me give you a formal argument why this should exist. And that's also answer your question about difference. So there are three groups in the story before I get to this one. Okay, there's a diff S2. Why I don't pay attention because they have no central extension, not trivial central extension. Now there's this ever preserving one. And the right analogy is that's the compact version. It's basically the version of SO2C versus SU2. And then there's this SO3. That's the fuzzy sphere given you, which is the fuzzy sphere Hamiltonian automatically have this symmetry. So anything you write down the model normally automatically have SO3 symmetry. So that's the beauty of this fuzzy sphere discretization. And now I want to take the point of view of like the famous, Nanny Steinberg and Moore-Gilbert, the Hilbert space of the CFT is constructed in this way. In the 2D version, left mover, right mover put together. And here, I want to treat this like the left mover, and this is the right mover. And what I want to do is get a representation here, and because inside here, automatically there's my conformal group, SO3 to there. That's this obvious field. And then what I would propose is that if you have a Hilbert space like this, constructed from representations here, and then you just write down the dilation generator here represent on that, that's your Hamiltonian. And that would be conformal. So is this related to the fuzzy 3D IC model? Maybe, maybe not. But we know the 3D IC is very different from 2D. It won't be conformal until you the limit. It won't be conformal until you have this very fine-tuned parameters. So that's a very difficult thing to study than 2D because you need both limit and fine-tune. So that's my proposal of this. And then the way I propose formally is that the fuzzy sphere model gives you representation of SO3. And that's actually generates, because it's a representation, it's go to SUN, and then SUN limiting to ever-preserving diffeomorphism. So I get representations of ever-preserving diffeomorphism. Then as a mathematician, I will do something very simple, induction. If a representation of a subgroup, you do induction. That's like a related automorphic form. If you induct onto it, that will give you a representation here, here. And then I have a loop, I need to take up a loop. And then this will be my left mover. And then I need to take a representation from the Virasoro algebra to cancel the central charge from here to make this anomaly free. And that's my candidate.
In this construction, wouldn't you expect a lot of integer space energies?
I actually Slava asked this question as his objection. I thought that it is not. This is the subtlety I didn't discuss. This is not truly a product. It's DVS2 and S1 because of the finite cover. They twist it together. It's just like a U2 versus U1 as U2. It won't be exactly integer space.
Can you repeat again, please? What is the...
So I know where this. So this is obviously the expert CFT people immediately object. What I said is that if you think about repetition of group G cross H, and then the repetition will come from residue G and the representation of H, and then cancel together. As a consequence, that would say any conformal field theory I construct have an infinite pair of primary field have an integer difference of scalar dimension. I'm saying I don't critique that it's because of the two group G and H. They don't commute. It's not that the group is a product. It's two subgroups. They actually have a common thing.
Oh, that's fine. But you're saying that in the end you get S3, 2 in this D that's 2 times S1.
I'm saying this is not the right formula. It's not a tensor product of this and that. That's what I'm saying.
So the summand in the direct sum is a honest representation of diff S2 times S1, which is not the same thing.
Yeah, it's not the same thing as this and that. There's a twist in here. On the Lie algebra, I won't see it.
Yeah, but I'm not worried about the tensor product. Are you predicting that this space of states is an honest representation of D of S2 times S1?
I'm not saying it's a faithful construction. I'm saying in this space I constructed to carry a repetition of this one.
linear representation of this group, and this group will have, more elements than the conformal group.
Yes, that's what I wanted.
Yeah, of course. So, does this group have a V algebra?
Yes.
So the generators of this V algebra, they will have the general, some integer scaling dimensions.
Yeah. Well, I know what they are saying. You are saying that all the things that are given in pairs of those kind of things. If I construct strictly
I'm just saying that the integer spacing in scaling dimensions would seem to me to come not from this tensor product and this universe, but just from the fact that you're insisting that this is a representation of V.
Okay, that's also fine. So the thing which I never understood is that nobody has seen any theory, including Ising, where infinite many pairs of fields with constant different scaling dimensions.
What do I want there?
Well, I don't know, but I'm just saying nobody has seen it. That's a strong objection to the possibility here. On the other hand, I just saying I'm not ruling out the possibility of them. I definitely agree.
But I'm just saying, like in Ising, we expect approximately 0 pairs of this kind.
Okay.
So,
That could be, okay, that's actually, I think I agree with, that's actually what Slava comment. Whatever theory constructed will brand new.
Could there be a reason why the spacing is very large, for example, and then you might not have seen it?
I would also possibly, we have not seen it, so yes or no. I'm just saying mathematically, I definitely see a possibility of construct those infinite dimensional representation. And then my Hamiltonian, you can also argue maybe Hamiltonian is non-unitary. There are lots of possibilities to be wrong, but I'm just seeing, I see a possibility. I think I will stop here.
Any more questions? Maybe last one, because you mentioned 40 TQFT and 3 CFT, so maybe if we go back to the two contemporary colored space. So at least in the 2v3 story, there's some discussion, at least there's some, this area, let's say whatever it is in 2v3 is encapsulated by some surface operator in the long 3. So you see some natural surface operator in the paper space that are on 40 TQFT.
No, actually, I was intended for a different. I don't know. This is not your question. Let me just say why I put this one up. So there are lots of discussion about TQFT, boundary conformal field theory in general. There also seems to be agreement that the 3D Ising corresponding to a TQFT, which is diagonal weighted. The trouble I have is I cannot see anything in diagonal weighted 4D TQFT will give you this amazing two transcendental number. Where that can be in diagonal weighted 4D TQFT has two of the scalar dimension. In 3D we know you see the scalar dimension in the exponent of the anyon topological twist. So whereas that's actually what I intended to say, which is if the thinking is correct, the Tory code has lots of things we have not seen.
On the factorization again, with that prefix, factorization. So the diff S1 part, you expect it to use, so the diff S2, and then this follows inside this bigger thing.
It could be. So I think actually that's what I was trying to say, which is if there's any chance this picture is correct, there are lots of these that in diagonal region 3 plus 1 TQT which recognize and everything. That's giving you transcendental scalar dimension, which is unbelievable if you had that.
Other questions? In the 2D CFT case, you raised the open space of the limit of the anyonic chain to a one-sided functions.
Yeah.
In 3D. So does that mean to do an analogous thing with 3D theory?
I don't know actually. That would be a very interesting because I think that's what ask how to do. I don't know. I just don't know.
Somehow the second part of the talk you didn't use much the generalization of the anyonic chain. Right?
Well, it is because I was imagining this whole fuzzy sphere. Why you even need fuzzy sphere? It's a too long. It makes there's something back in my mind I always want to realize, which is Polyakov said 3D Ising model is a free from Young loop. So the way I want to pursue is the two-sphere is a sequence of loops. I want to make the model flow to 3 fermionic loops. So it's a chain of